Hello, in this video we want to talk about introduction to tensor analysis. But before we go into that, we want to discuss what tensors are. As a way of introduction, tensors are generalized mathematical objects that extend scalars, vectors, matrices to higher dimensions. They are fundamental in physics as regards to general relativity, in computer science, in areas of machine learning, and in mathematics, like in differential geometry, as well as linear algebra. Now, these tensors, there are two types or two categories of tensors. And that is to say that tensors can be categorized based on one, the rank, and two, their variance. So let's look at the categorization of the tensor in terms of ranks and in terms of variance. Now, based on rank, if you want to to classify tensor in terms of rank, one, we start with zero rank tensor. Zero rank tensor. Under zero rank tensor, the example of that is scalar. Scalar comes under that. Okay, we have one rank tensor. One rank tensor. Under this, we have vector. Okay, we have two rank tensor. Then under this, we have what? We have matrices. Okay, we only have higher ranks. That is the one that is more than two. Higher rank tensor, higher rank tensors. So under this, we have stress, strain, and line. Stress and strain, and stress and strain. Okay, and a host of others. So these are the ranking of tensor. Based on their types. We have shown here that this form one of the methods or one of the yardsticks for classifying tensor. We have in terms of rank now. Now let's look at tensor in terms of variance. Tensor in terms of variance. Let's look at tensor in terms of variance. Okay. In terms of variance, we have three comes under play here. We're going to discuss three. We're going to analyze or state three examples of tensors in terms of variance. Tensor in terms of variance. Okay. Now under this, we have one. We have covariant tensor. Covariant tensor. These ones are what? They are what? Covariant tensors are subscripted. They are subscripted. Tensors are subscripted. I will explain to you what I mean by subscripted. For example, now, if I write this is an example of, you can see that the subscript P is below. I can write Aij, where I and J are subscripts. So this is an example of covariant tensor. Okay, now contravariant tensors. Contravariant tensors. These are superscripted. Superscripted. From the word superscripted. E.g., you can have this as we have Aij can come up here. Okay, that is the indices I and J are on top. That's what they are subscripted. They are superscripted. Okay, but the one that's lie below that come down instead of being up are regarded as subscripted ones. So those are called covariant tensors. Now we have mixed tensors. Those one contains what? Both contain the superscripts and the subscript contains subscripts, subscripted indices or index, and superscripted one, superscripted index or indexes. Example, here I can write AIJK. You can see this one, it contains what? It has the indices as it has the superscripted indices as I and J, and subscripted K. So these are mixed tensors. So those are the two major categories that we can put tensors in. That is, we can put them into what the ranking, and we can also discuss them about. We can put them in terms of variance. So let's continue. So having seen the two ways by which you can categorize tensors, let's look at how tensors can be transformed. Transformation of tensors. But it will be pretty better if we start with the coordinates of transformation. Coordinates of transformation of tensors. So let's look at let's start with coordinate transformations. Coordinate transformation. Coordinate transformations. Okay, this is an important aspect of tensor analysis, because it has to do with trying to move from one frame of reference to another. Now, by the word coordinate, we must have come across this word in mathematics, particularly under coordinate geometry, where we're talking about geometry of a space, of plane, and the like. Then we'll be talking about x, y plane, x, y, z plane. So also in tensors, we have seen the examples of tensors now as scalar, as vector, as matrices, and we have strings and strings, and the like. Now we can transform. We can change our frame of reference from one, coordinate point, or from one coordinate to another. I'm trying to say that if we are given a certain quantity in tensor, we can transform from one frame of reference to another. Let's look at it from this definition. So let's say that let's x1 x. These are not exponential. They are like indexes. Okay. So xn b. Okay, and let's combine the two now. X bar 1, x bar 2, x bar n. This let them be coordinates. Let be coordinates. Let this be coordinates of a point. Let's do 2 points, the coordinate of a point in two different frame of reference. In two different frames of reference. What do we mean by frame of reference? Our frame of reference could be, for example, a rectangular plane. It could be a cylindrical one. It could be, just any frame of reference. It could be elliptical. So that's what by frame of what? Reference. Okay. Now suppose there exists. n independent relations between. Suppose there exists between the coordinates of the two systems, that is the two frame of reference, having the form. Now, the first one could be written as, let's say, x bar 1, which will be x bar 1 there's a function of x1, x2 to xn, comma here, dot, comma, xn. Okay? Now, that is, you can see that we are having two coordinates, these and these 2 points. Now we want to show something. Just relax. So the next one will be what? X bar 2 is equals what? X bar 2 of the same coordinates. Okay? And until we get to x bar n, which is x bar n of the same coordinates. If you observe closely here, I see that we are talking about n independent relations. So we have n, dimension of the coordinate is n. Okay. Now that can be, all this can be indicated briefly by, you can summarily write this as, instead of writing these lengthy things, let's look at how we can summarily write this. This could be summarily written as, that can be indicated simply as, can say x bar k, is equal to x bar k of x1, x2 till, xn. So in this case, that means our k is from 1 to n. Okay? All right. Now, so that is supposed to be here, and in this case now, our function is supposed to be single valued, is supposed to be continuous, and supposed to have continuous derivatives. So in this case, this function, is single valued because depends on this. Okay, that is, instead of writing this out, we can summarily write this, which everything here is being what? Compressed as this. Okay, now then conversely, let's look at the converse aspect. Now this is one aspect of it. If we transform from one frame of reference to another, this is how it looks like. Okay, now we started the definition with the one with ordinary x1, x2. Now we move towards the one with bar. So now if we are transforming from the one with x1, x2 to the one with bar, that means the bar is going to be the starting point when we are transforming. We actually started from x, and what I'm saying is this. We started from x1, x2, that's the coordinates given to us in the statement. In this example, now we are given the second coordinate to be this, and so on. Now, that means the starting frame of reference is this, and it's the final one. So by the time you want to transform, you start with the final one. Okay, so you swap it. That is the idea. Okay, now let's look at the other one. Now conversely, suppose that I want to, to each set of coordinates, okay. Let's write this out. Let's clean this. Okay. We can have, so instead of coordinates x bar 1, x bar 2 to x bar n, there will correspond a unique set, of course, a unique set. I give this note fit so that you'll be able to have a comprehensive understanding of what I'm teaching. Okay, I want you to understand everything in details. That's why I'm writing the notes given by, because we are going to illustrate all this with examples, but I want you to have an idea of what we are talking about. So we can have given by x raised to power k to x raised to power the index, x bar 1, x bar 2, x bar n. Okay, and that is where k, I've given you what k stands for. K is 1, 2 to n there. So now this is another relation. You can call this relation 2, and let's call this relation 3. If you look at this closely, you just see that this is just like a transposition of this. Okay? Now, like I was explaining the other time, we are given two coordinates. Coordinate x1 to xn and coordinate x bar 1 to x bar n. Those are the two coordinates given to us. And I said that we started with this coordinate. This is the second one. So when we want to transform from this coordinate to this second one, we start with this second one. Okay? Now, conversely now, that means we are starting with this one. Okay? So that is it. So when we started with, this is the initial coordinate, this is the final one. So when we want to transform from this coordinate to this coordinate, we started with the bar one. Okay? That's x bar k is equals to x bar k of this one, where your k is from 1 to n. Okay? Now, if you now want to find the converse aspect of it, you start with this one. That's why we have sk, is also sk of s bar, where you have your k to be 1 to n. So let's look at because I don't want this video to be too long, because we're going to have a series of this particular class. This topic is going to be taught in series, because the whole lot of this topic could not be taught at once. And to allay the fears of students who have always been, running away from tensor analysis, I've deemed it fit that I want this lecture to be very, very comprehensive and to be made in series. I am Dr. OJ. God bless you. Now let's look at the summation convention. The summation convention. The summation. What do we mean by summation? Summation convention. Okay? We are going to see it now. Convention. Now, you see, let's say A1x1 plus A2x2 plus and so on plus ANxN. You can write it briefly. Be put as. You can say that be put as summation, A, let's say I, J, I. Sorry, xi, or I can write j here if I like. I can write aj xj, where my j is moving from 1 to n. This whole lot of this has been put as a form of linear combination. Okay. Now I can simply write this if I don't want to, based on the convention given. I can simply put this on in a form of aj xj, where I assume that my j is from 1 to 1 to n. Okay, this idea is what we call summation convention. Summation convention. You observe here that j is repeated, okay, and is governed by what we call summation convention. So since this j is repeated here, that is j happens to be a substrate and at the same time what? A superstrate. Then we say j is a dummy index. A dummy index. We call J what? A dummy. A dummy index. A dummy index. Because it is what? It is repeated. Not only that, at the same time, it is governed, or it's moderated or related by the summation index. Now, if you look back at example, the equations I have in 2, where I have, I think in 2 I have x bar k, can you still remember? X bar k over x bar x raised to power 1, x raised to power 2, till x raised to power what? N. And I said my k is equals to 1 to what? To n here. So that is equation 2. So you go back to equation 3, I have what? X, k is equals to sk over x bar 1, x bar 2 to x bar n. Yes. I said k is the same thing there. So this k here is what? It's called a free index because it appears only once and it's not repeated. You can see. So it's called what? As illustrated there, it is called a free what? Call it a free index. It appears once, it's not repeated, and it's not related by the summation convention. Okay. So let's look at let's try to stop this video here so that it will not be too long. So in the next video we shall continue with contravariant tensor and covariant tensor. We shall look at the difference between the two of them. So I remain Dr. OJ. Don't forget to click on the notification bell so that each time I upload a new video, you'll be duly notified. And always try to share and like this video. Thank you. God bless you.